Next section is the fully developed laminar flow. There are three ways to derive equation for the fully developed laminar flow. The first method is we use the second law of Newton, F equal to ma, and the second way is use Navier-Stokes equation, but we don't show here. And the third method is the dimensional analysis. Okay, start from the F equal to ma. This below figure is a cylinder of the fluid. The length L is a length L, and radius R. This is a radius R, and this R is the radius of the pipe. The center on the axis of a pipe is diameter d. That is the pipe diameter d. Velocity is not uniform across the pipe, so that is the velocity profile. Okay, for across the pipe. Initially, flat end of the cylinder of the fluid at time t become distorted at time t past delta t. In case of we draw the control volume in the blue color, in the some like green color, and this is element of the fluid at the time t. At this, the dash line is the element at time t plus 1. So the system of the fluid is distorted at time 3 past delta t. And then below figure, we show the fluid diagram of the control volume of the fluid of water. Pressure drop. You can see the pressure decrease in the direction of flow, and delta P is greater than 0. Okay, and shear stress tau act on the surface of the cylinder. Okay, that is the pressure, the force on the left hand side, the force on the right hand side. And consider the shear stress on the surface. Okay, we apply the F equal to ma and assume that the acceleration is equal to 0. So and develop the horizontal pipe flow is in balance between the pressure and viscous force. Okay, that is the equation of the summation of force. In this case, we can prove that delta P pi r square is equal to 2 pi r L tau. So this equation is on the left hand side. Okay, and from this equation, delta P divided by L equal to 2 pi tau r. We can derive this equation. And we can understand from this that if R is 0, so it means the center of the pipe there is no shear stress. Okay, the shear stress is 0. And if the R is equal to d over 2, at the pipe wall, the shear stress is the maximum, and denote that the shear stress is equal to tau W, wall shear stress. And in this case, can prove that shear stress is the linear function of the radius coordinate r. Okay, and that this shear stress is equal to, we can write another way, that is the ratio of the r divided by d over 2. Okay. And below figure shows the linear dependence of the shear stress, and R is the result of the pressure force being proportional to the R square and the shear stress being proportional to R. That is, show the linear proportion of the shear stress with the R. Okay. And if the viscosity is 0, is no shear stress, the pressure would be constant throughout the horizontal pipe. Okay, so we expect that the pressure distribution is like this. Velocity profile is constant throughout the cross section of the pipe. And then next, the pressure drop and wall shear stress are related by this equation. It is from equation 1, and it assumes that we use the d equal to r equal to d over 2. And then next we apply the Newtonian fluid, okay, for the relationship between shear stress and the velocity gradient, okay, and this show the equation for Newtonian fluid we learned from the property of fluid. Negative sign include to give the shear stress is greater than zero and the velocity gradient is less than zero because the velocity decreased from the price center to the pi wall. We combine equation 1 and 4 together, so we got this equation and substitute tau from equation 1. Okay, and we do integration to get the u is a function of the r square and plus the constant c1. The fluid is because if the stick is to the pi wall, so that u is equal to 0 and r equal to d over 2, so we can find the constant c1. And finally we write the equation of velocity profile. U is a function of r. This is a vc and this is r square. Okay. In this case, if r is 0, so ur is equal to velocity is equal to vc. Vc is the center line velocity. Okay, that is vc, center line velocity or the maximum velocity. The next step, if you want to find the flow rate along this pipe, you can do integration of u dA. Okay, dA is equal to 2 pi r dr. Okay, this r is the small length of radius. And we substitute u in this equation and got this equation. But if we don't know how to do integration on this, we can use the basic knowledge from calculus that in case of the Q is equal to area times U average. Okay, U average. In case of we learn from the calculus that for parabola shape of the distribution, U bar is just a half of maximum velocity at Vc divided by 2. So in this case, we can use the Q is equal to the area pi r square divided by Vc divided by 2. Okay, and for VR, V average is equal to this term. Okay, and because Q is equal to V prime time area, so we just time area to the V average. So we got this equation. So this equation is for laminar flow. Okay, the next step is adjustment necessary to account for what we non-horizontal pipe is shown in below figure. In this case, if we derive from equation 1, they add one term, gamma L psi L is equal to 2 shear divided by R. Okay, then you can see that add another term here. Okay, so where this term come from? This term come from the, you can see from the W psi theta. Consider this one W psi theta. Okay, W psi theta we can substitute mg psi theta, and for mass is equal to rho times the volume, and we substitute volume pi r square L. Okay, so we got this term is equal to rho g gamma and pi r square L psi theta. In case of pressure, we divide this term by area. So finally, we got this term. The increase of pressure, the subtraction of pressure is gamma L psi square psi theta.